I'll start now. So we've had 6 lectures on scalar fields, and I think that's enough for the time being, and I'll move on to vector fields today. So what did we do in those 6 lectures? We laid out some basic framework of quantum field theory, and we showed how in perturbation theory amplitudes can be calculated or correlation functions can be calculated as an expansion in terms of Feynman diagrams. Now, from that we didn't calculate anything which can be compared with experiment, and that's partly because the only particle in nature which is believed to exist and which is a scalar is the Higgs particle, but it hasn't been discovered yet, and so there's no direct experiment we could compare any of those things with. So instead of going down that route, I'll now introduce fields which correspond to known particles, very familiar particles, and then we'll come back to the question how to connect correlation functions with physically observed quantities. The definition of correlation functions, that is time-ordered products of fields, will be very parallel in these cases to the one that we gave for scalar fields, with some little subtleties now and then which we have to go through. So I hope the strategy is clear. In this sense, the last 2 or 3 lectures of this course will be sort of back, we'll have a focus back on actual calculation of useful things. Okay. Now we know that under Lorentz transformations, a coordinate x mu goes to x prime mu, and I think you've seen the properties of this matrix lambda, that lambda transpose eta lambda is equal to eta, and a scalar field was a field such that phi prime of x prime is equal to phi of x, where x prime is that. So it said that it retains its form in all different Lorentz frames. What's a vector field? The natural definition is to say that it has one index, just like the index of x, and that a prime mu of x prime is equal to lambda mu nu a nu of x. What has happened is that not only x prime has gone to x, but the vector a has got rotated, or in generalized sense rotated, because this includes rotations as well as boosts. It's got Lorentz transformed. So it's a natural definition, and this is a different type of field because it has 4 indices, unlike the scalar field, and because we cannot really ignore any of them, because the fact that you have 4 vectors is tied to the fact that we have 4 space-time dimensions. Mu goes over the values 0, 1, 2, 3. So in this case, the index is absolutely essential to the properties of this vector. A simple exercise, which you can do if you like, but we won't even need it, is that if you lower the index mu, then a prime of x prime is lambda inverse transpose mu nu. This is just an exercise in properties of lambda. Take its gradient, del mu phi. This quantity occurs when we build the Klein-Gordon Lagrangian or Klein-Gordon action, and this transforms exactly like this. It's easy to check. It must. All quantities with one lower vector index will transform the same way, or if I raise that mu with an eta mu nu, then it will transform like this. And it will turn out this property that del mu phi transforms like a vector field will have some important consequences. But of course, the vector fields we want to study are not of the form del mu phi. They are just independent vector fields. Not necessarily of this form. But that form shows that such things do exist. Okay. Now, the normal process is to guess some field equations and derive and argue backwards to get a Lagrangian. But by now, we have learnt enough about Lagrangians, so better to guess the Lagrangian and then get the field equations from that. So let's try to guess a Lagrangian. Now there's one very obvious guess for a Lagrangian density, which is to say, well, this really looks like 4 components, each of which is roughly like a Klein-Gordon field. So if we just copy what we did for the Klein-Gordon field, hopefully it will work. So in this approach, I would say let the Lagrangian be del mu a nu del mu a nu. There could be a mass term, but I'll come back to mass later. Let me just work with the free massless field. So, and of course there could be interactions, that also we'll look at later. So let's try this. This won't work actually, but it's reasonable. It's a copy of the Klein-Gordon action Lagrangian if I had just put pi in place of a. And I've just contracted the indices. So the equation of motion this gives is del mu a nu equals 0, which is one independent Klein-Gordon equation for each component. Right? So far so good. Now this theory, as soon as we try to quantize it, has a serious problem. So let me show you the problem. So let's calculate the canonical momentum conjugate to the field a mu. So we'll call it pi mu, and this will be delta L by delta a mu dot. By now you know how to do this. So a dot occurs when this is del 0. So we pull out del 0 again, and the factor of 2 comes because it comes in 2 ways. So it's just a dot. Okay. Now the commutator is phi with pi equals delta, I times delta. So here it must be a mu with a nu dot, and we would like this to be I, and it should have delta 3 of x minus x prime. But of course there are different indices mu and nu here in principle, and these transform under Lorentz transformations, so the right side should have something Lorentz invariant. So what is that? Not Kronecker delta, but eta. Has to be eta, and that's the key problem. So the right side has eta. Okay. Now remember that from here you get some oscillators. That would be the next step. We would decompose this into oscillators. And from here the oscillators would inherit a relation. So the oscillators would be a mu comma k. And a dagger nu comma k prime. So this would be 2 pi cubed. Again the eta would be there, and delta 3 of k minus k prime. So far so good. Now let's notice what is the problem. What is eta? Eta is diagonal 1 minus 1 minus 1 minus 1. So while a naught with a naught dagger is 2 pi cubed times delta 3, ai and aj dagger have a minus sign on the right because of this eta. So that's very unusual. So A I K A J K prime dagger is negative. This is very, very bad. Let's see why it's bad. It's bad because consider the state, the one particle state, A dagger IK on 0. I is one of the three space indices of this vector field. Okay, it's just when mu takes the value 0, 1, 2, 3. I is when we specialize it to only 1, 2, 3. So this should create three possible types of particle with momentum k. So far so good. What's the magnitude or norm of this state? To calculate the norm, we put the same thing on the other side, AIK. And then we use the trick that this can be replaced by a commutator. And now we have a problem because the commutator, when this is I and this is I, is negative. Okay, there's a small extra problem, which is that if these two are equal, then we get delta of 0. But we've understood that you can do all this in a box where you just get Kronecker delta. But the point is that this is negative for the reason that that is negative. And this is the norm of A dagger I K 0. So physically that's very bad. It means that this theory has states of negative norm. Norms are related to probability. That means that this theory will have negative probabilities and it will be inconsistent. The equation of motion doesn't change. If we go here, then pi is minus A dot. So this with this is minus I eta, and this is also minus. Yes. So now instead of having a problem with AI AJ, the problem is transferred to A0, the time component of the vector field. So at least you can say it's a problem with only one out of the 4 components instead of 3 out of the 4. That's why we say it's better. So norm of A naught dagger is negative in this sign choice, and we still have an inconsistency. Yes?
If you have a negative sign in the commutator, wouldn't the behavior of A dagger change? In other words, A dagger is actually a destruction operator.
No.
And A may be a creation operator.
Not really. Yeah, the point is, you could try that, but then you see it would violate Lorentz invariance because you would want A to be a destruction operator for the space components, but then you would say let A dagger be destruction operator for the time component. That means by Lorentz transformation, I don't rotate destruction into destruction operators. So whatever you do, it's a conflict with Lorentz invariance. Okay. Yes. Yes, different in sign, that's why this is not good. I just took the naive sign plus to start with. Now I've taken minus, and now I'll see that of all things, an experimental result tells us how we should change that sign, change that Lagrangian to get a consistent Lagrangian. There exists a particle that should be described by a vector field, that's the photon. Okay, its vector potential A and scalar potential phi together combine to form a 4-vector field. And the equations of motion for the known phi and A, which we'll call A mu. So these are Maxwell equations. And these are del mu A nu minus del mu A mu equals 0 in free space. We're doing everything in vacuum. I hope this form of Maxwell's equations is familiar to you, otherwise this is the first exercise you should do in tutorials. Okay, it is this structure which gives you curl of E and curl of B and so on. And all those curls which appear in Maxwell's equations come from this. This is also a curl. Anything which is anti-symmetrized derivative can be called a curl, and this structure is what you get.
So,
Yes.
shouldn't it be equal to del mu F mu equal to J mu?
Yes, so I said it's in vacuum. In vacuum, J mu is 0.
In vacuum, I was wondering if there should be a epsilon Levi-Civita tensor also with contracted with F mu. Del mu epsilon.
No, that's another equation. That's an identity. This is Maxwell's equation. You can check directly that this is Maxwell's equation. In vacuum, first of all, in vacuum, so you're right, it should be del mu F mu nu equals J nu. But in vacuum, J nu is 0, therefore it's del mu F mu nu equals 0.
Okay, I had in mind that it was del mu dual F mu equal to 0.
Yeah, that's another equation that gives some part of Maxwell's equations. Okay, there are 8 Maxwell equations altogether, 3 plus 3 plus 1 plus 1. 4 of them are dynamical equations, which are these. The other 4 that you're talking about are identities. Okay, so I won't be using those. I just need this. I just need 4 equations to determine 4 variables A mu. Okay, and you're familiar with the fact that this is called F mu nu. It's just a definition. And the corresponding Lagrangian from which you get this is minus 1/4 F mu nu, F mu nu. So it's minus 1/4 del mu A nu minus del mu A mu, del mu A mu minus del mu A mu. Okay? So this is the Lagrangian that gives Maxwell's equations. Now I can expand it out. There are 2 terms and 2 terms, so totally 4 terms. Okay? If I take this with this, or the second term with the second term, I get the same thing. I can just flip the indices, and that same thing is minus half del mu A nu, del mu A nu. Next, if I take this with this, or that with this, these are terms with an opposite sign. Minus with this minus gives me plus. So I get plus half del mu A nu, del nu A mu. Notice that these 2 terms differ because of the way the indices are contracted. Here the derivative has its indices contracted and the gauge field also, while here derivative and gauge field are contracted, derivative and gauge field are contracted. So it's different. Now you see how closely this resembles the Lagrangian we tried over there. It just has an extra term, which is this term. Then this one. The second term, in a Lagrangian I can't do much, but if I was integrating the Lagrangian in 4 over d for x, then I could do integration by parts to take these derivatives to the other side, dropping some surface terms. And those kind of terms have no effect on equations of motion. So if I do that, it's a very simple exercise to see that the extra term is del mu A mu the whole squared. Divergence of the vector field whole squared. Why? Because this del mu by partial integration goes here with a minus sign, then this one comes here with another minus sign. That's all. Yes?
These manipulations will not alter the equation of motion.
Yeah.
But the energy momentum tensor
Yes.
will change.
True.
So is that okay?
Yeah, it's okay. I mean, we have no prejudice for it anyway. And there are many energy momentum tensors, so depending on the situation, there are many ways to define it. This is a classical theory, so we can add a term whatever way we like. So this is the term. So now I claim that this extra term will solve all the problem of negative norm states. Okay? So here's an interesting situation that a theorist who was just trying to repeat what they already knew would have only guessed this term. But an experimentalist gave us an answer which involves this extra term, then theorist says, yeah, this is also possible, I never thought of it. So you add it, but of course even then you wouldn't have known with what coefficient to add it, but the experiment has told you very clearly that this is the coefficient to add with. So this is the action of that gives rise to Maxwell equations, and now let's try to see that this action actually solves our various problems. And for that, let's again compute pi mu, which is delta L by delta A dot mu. Earlier we had got just minus A dot mu from the first term. If you combine with the second term, you realize that what you get is minus F0 mu, which is the same as minus A dot mu minus del mu A0. Is that clear? That F0 mu is that? This definition. So we have a new term in the momentum, in the field momentum. Okay. Now which was the one that was problematic? Was pi 0, because that was giving negative norm states. So now let's see in the new theory what is pi 0. So what do you get by putting mu equals 0? 0. Pi 0 is 0. There is no pi 0. So we learn that A0, the field, the component A0 has no conjugate momentum. And this is a strong hint, though it's not yet a proof, that there won't be any problem with negative norm states, because in fact, as we'll now show, A0 of Pnx is not a dynamical field. We'll make it more and more clear what we mean when we say it's not a dynamical field. Okay, it's some kind of artifact or some kind of artificial variable, field variable, which can be removed. The old one is a property of Gage invariance, which I'm sure you have heard of and even worked out perhaps. And it is the fact that under A mu goes to A mu plus del mu lambda, where everything here depends on all four coordinates of space-time. Then F mu nu goes to what? Del mu A nu plus del mu lambda minus del nu A mu minus del mu lambda. And because derivatives commute, these two terms cancel and it's F mu nu again. So there's a symmetry under which F goes to itself. If F goes to itself, then minus 1/4 F mu nu also goes to itself, and the Lagrangian is invariant. And this is the first example and the most basic example in field theory of a symmetry or invariance with a parameter that depends arbitrarily on space-time. Whatever is lambda of x, it doesn't matter. Any function lambda of x, these two terms cancel out. Lambda is not required to be, for example, constant or anything like that. For any function lambda of x, this symmetry holds. Okay. Now, this is rather troublesome, because if you think what does it mean, it tells you that a configuration A mu and another one A mu plus del mu lambda have the same Lagrangian. And this is not just a finite parameter set of configurations, okay? Because lambda of x being an arbitrary function, I can take any configuration A mu and add to it a huge infinity of other configurations del mu of lambda for all possible lambdas, but it will have the same Lagrangian and therefore it will inherit the same dynamics. So after many years of studying this problem, it has been understood that this is not a symmetry at all, in the sense that we use the word symmetry. It's better to call it gauge invariance rather than gauge symmetry, because symmetry relates to physically distinct situations. For example, if I'm facing this way in a vacuum and I face the other way, then by rotational invariance, these two situations are symmetric. Okay. However, you can't say that physically it's the same, that I'm facing this way, I'm facing that way. For example, if I have two people, one facing this way and one facing that way, it's clear that these are different people, or they are doing different things, but the laws of physics applied to both of them are the same. That is symmetry. Here it's something different. It is that A mu and A mu plus del mu lambda should be treated as the same configuration. And in fact, you know this from electrostatics. Okay, because in electrostatics or electricity and magnetism, you might solve for some magnetic field B for some situation, and then for some solenoid or something, and then from B, if you try to solve for A, the 3 vector A, you'll never find a unique answer. Okay, because B is curl of A, and if you know B, then you know A, but you can shift A by gradient of a scalar, and you will still get the same A. So what shift is that? It's just this, if I look at it in 3 vector notation. The 3 vector potential can shift by gradient of a scalar. Okay, so we conclude from this that this is a redundancy of the description. By redundancy I mean A mu and A mu plus del mu lambda are the same physical configuration. Mathematically they look different, but physically they are actually the same. Gave you with simple electrostatics or magnetism. Here also you can say, well, these two lead to the basic field variable and not f. So we have to live with the fact that A mu of x is a basic field variable, as well as A mu and A mu plus del mu lambda correspond to the same situation. Somehow we have to live with that. Yes? Yeah, f mu is a field, but it's a field defined in terms of A. Yeah. Only if I define it in terms of A, then I can get the Maxwell equations from that Lagrangian. So A is the basic variable appearing in that Lagrangian. I can rewrite the Lagrangian as minus 1/4 f squared, but f is given in terms of A. It's not possible to forget that.
That's because you're basically saying that f mu has to be something according to Maxwell's equation.
Yes, exactly.
If I forget that thing, f mu is some field.
Okay, very good. What Lagrangian will you write for it? Good, f mu nu squared. So what equation of motion will you get if your Lagrangian is f mu nu squared and you... Sorry? Exactly. That's the question I'm asking you. You are proposing that f squared is a Lagrangian where f is the basic field. So a good idea, you should follow it. Now in that Lagrangian, you will see that the equation of motion, if I vary f mu nu rather than varying A, equation of motion will be f mu nu is 0. That's not very interesting. That means all my fields are 0. That's not the Maxwell equation. Maxwell equation is that f can be non-zero, but del mu of f mu nu should be 0. So in order to get the correct equation of motion, I must use the correct Lagrangian. You can try any action you can think of which gives the correct equation of motion, but you will see that sooner or later it runs. Why the problem of negative norm states goes away. Okay, so we should not think that gauge invariance is simply a pain in the neck because we have to consider so many different configurations that all correspond to the same one. It's also a benefit because essentially it's the only way to have vector fields and get rid of negative norm states. Because you saw that if we don't add this term, then this has negative norm states. And if we add this term, Supposing we change the coefficient by a small amount, then it wouldn't have gauge invariance, but nor would this be like this. There would be a small difference between these coefficients, and for the momentum for A0 would not be 0. Pi 0 is 0 exactly because of the correct coefficients for these two terms, which comes from the coefficients for these two terms. So exactly when it has gauge invariance, then pi 0 is 0. Pi 0 is 0 as a consequence of gauge invariance. In passing, let me mention two things. One is, instead of vector fields, perhaps we could consider tensor fields, okay, fields with more than one vector index. All such theories have the same problem of negative norm states, not just the vector field theory. Why? Because as soon as your oscillators A and A dagger acquire some number of space-time indices like mu, nu, lambda and so on, then there will be some combination of them which will have negative norm. Is that clear? The problem of negative norm comes because time and space have different signature. That in itself comes from relativity. Okay, so we are bound to get that problem. In fact, we escaped it narrowly only because we had scalar fields earlier, which had simply no transformation under Lorentz transformations. As soon as you have any vector or tensor field, you have potential problem of negative norm states. So it means any theory involving vector or tensor fields must have gauge invariance in order to be consistent. So this is a very important result, that simply there is no consistent quantum theory without gauge invariance for such fields. Okay. There is no analog of this kind of result in non-relativistic quantum mechanics, and these kind of constraints come because of the structure of relativity. So that's one remark. Second remark, we didn't put any mass, but let's think of a mass term. This would be a mass term, just like m squared, phi squared for Klein-Gordon theory, maybe with a half, maybe with a minus. Okay, but what effect does this term have on gauge invariance? It's not gauge invariant. This tells us that in this theory, adding such a mass will lead to an inconsistent theory, because not being gauge invariant, then at the end we won't be able to decouple negative norm states. Okay, gauge invariance is sort of an absolute principle. Yes?
So actually it's not clear to me, when we got to the appropriate Lagrangian, where have we used gauge invariance? It just comes out of the form of Maxwell Equation. The form is such that it should not depend on the gauge quantity.
Yes, yes.
So we have not somehow explicitly used the fact in getting to the Lagrangian that there should be gauge invariance.
No, in fact, the Maxwell route is to first find the Lagrangian from experiment, and then you notice that it has gauge invariance. Okay, each law of Maxwell, which are four different laws, curl of E, curl of B, del dot E, has gauge invariance. Okay, that we notice, and then it's built into the Lagrangian. However, if you want to take the other approach, you will get the same result, because given that A should transform like this, the unique combination that doesn't transform under gauge transformations is F mu nu. So you will be inclined to build your Lagrangian out of F mu nu only. Once you do that, then the square is the natural one. So you can also derive the Lagrangian starting from gauge invariance. It's a question of which is the original point of view. Of course, this thing all started with experiments on electricity, but now we think of it from a sort of more abstract theoretical point of view. Okay, so this is not gauge invariant, and because this is not gauge invariant, it suggests, though it doesn't prove as we'll see later, it suggests that the vector field should be massless. Now you see, this is an experimental, this is a prediction that can be verified. It means if we look for any vector field in nature, any particle described by a vector field, it should be a massless particle. And the first place where it's tested is the photon, which is the quantum that you get, the particle that you get by quantizing this vector field, and indeed it's massless. So you feel very happy. That means the masslessness of the photon is due to gauge invariance. Okay, this was the picture perhaps early in the 20th century, and it also says that, of course, experimenters may keep looking for a tiny mass, because when mass looks like zero, it may be some tiny quantity which we haven't found up to now. But it suggests that those efforts are in the wrong direction, because gauge invariance is fundamental reason. Without it, the theory will simply break down. So maybe it is just true that the photon is exactly massless. Unfortunately, today we know 11 more vector particles in nature, W and Z bosons, 3 of them together, and gluons, 8 of those. And none of those is massless. Okay? And that's due to 2 mechanisms which are not anticipated when we write this. One of them is called Higgs Mechanism and other is called confinement. Both are ways around this, can get around this. And in fact, it's interesting that these are the only mechanisms we know, and one of them is used by weak interactions, while the other one is used by strong interactions. These things we'll come back to at the end of this course. For our present purpose, we stick with the fact that you simply can't add a mass term, and so we are going to study quantization of the free Maxwell Lagrangian. Without the addition of a mass term. Or maybe one comment I forgot to make about gauge invariance is just a simple observation. Supposing I take A mu and send it to A mu plus del mu lambda 1. Lambda 1 is some chosen function. And then I perform another gauge transformation. So this A mu goes to A mu plus del mu of lambda 2 plus del mu of lambda 1. So I'm performing 2 gauge transformations. First lambda 1 and then lambda 2. Supposing instead of that I perform them in the other order. First I perform lambda 2 and then I transform A mu by lambda 1. You notice that both ways I get the same answer. In mathematics, when you perform 2 operations which commute with each other or give you the same answer independent of the order, then those are called abelian. Okay? So this is actually abelian gauge invariance. And for the rest of today, it's the only case that we are going to study. In fact, for the next 3 lectures, we are only going to study this case. So the Maxwell equation system has abelian gauge invariance. Okay. Good. Now, to quantize, that is to make a quantum system out of this, we have already seen that A naught has no canonical momentum. Pi naught is 0 in this system. So right away our whole plans of quantizing seem to break down. What should we do? A naught is there, but pi naught is not there. So what should we do next? We can't ignore it because A naught is there, and we can't quantize it because pi naught is not there. So the solution, and this is the general rule, is that in order to quantize, we must fix the gauge. Fixing the gauge means the following. Given any configuration A mu, I apply a gauge transformation to it to bring it to some standard form. Thereafter then I am not able to make any more gauge transformations. Okay? So that will enable me to work with the genuine physical degrees of freedom, and it will also exhibit for me which degrees of freedom can be taken away by gauge transformations and which are really there. Now there are many ways to fix the gauge, and when we fix the gauge, then our we have to make a choice whether we want to respect manifest Lorentz invariance or not. Both of these have advantages. So now I am going to go through two ways of fixing a gauge. One violates manifest Lorentz invariance and it's called Coulomb gauge. And the second way, which I'll do later in this lecture, is called Lorentz gauge, and it preserves Lorentz invariance. Finally, all physical results will be Lorentz invariant. So it's only question whether in the intermediate steps we violate Lorentz invariance or not. Coulomb gauge is very nice and very natural for the following reason. Let's look at the gauge transformation separately for A0 and for AI. Okay? And let's ask ourselves the following question. Wouldn't it be nice if A0 could be brought to 0 by a gauge transformation? Because then we would solve that problem. Remember, A0 had no canonical momentum. So it's best if we can take it to 0. And you see that all we have to do is choose lambda such that del naught of lambda is minus A0. So, choose lambda of t and x such that del naught of lambda is minus A0. So for any fixed configuration A0, we make that gauge transformation and it goes away. How do we find lambda like this? Very easy. So that means that lambda of t and x is simply minus integral dt prime A0 of t prime and x up to the limit t. Lower limit doesn't matter. If I differentiate this, I find that del 0 of lambda is minus A0. Okay. So using this, lambda, this is a common usage, gauge away A0. Set it to 0. So now our system has only 3 A's. Okay. Now, is there still gauge invariance or we have completely fixed the gauge invariance? Can you see from the equations on the left? Those equations. Once I have gauged away A0, I can't make any more gauge transformations which will bring it back. If I make any gauge transformation without thinking, it might bring back A0, which I have sent to 0. When will it bring back A0? Which kind of lambdas bring back an A0 when it's already 0? Time dependent. If lambda is time dependent, then del naught of lambda is non-zero. So even if this was 0, after performing a new gauge transformation, it will again be non-zero. So, but I can still consider time independent lambda. So only of x, doesn't depend on t. Okay, and I can still send ai to ai plus del I of lambda of x has been set to 0. So there are two sets. One is when nu is equal to 0, another set is when nu is equal to I. So mu equals nu equals 0 gives del I fi 0 equals 0. And what is fi 0? So many answers, there can't be so many. Only one possible answer. Yes, what is it in terms of A? These are all equations for A. Minus of A vector, no. Yes, I know that, but I want it in terms of A. Del cross A. Del I AI. No, I'm asking only what is Fi0. Yes, but we have set A0 to 0. So now, finally, AI dot, brilliant. Okay, so this is del I, so this is del 0 of del I AI. Okay? This is AI dot, up to a sign, I'm not interested, I'm putting this to 0. So this is AI dot. So del I, del 0 of AI, but these two derivatives I can interchange the order. So the equation of motion tells me that del I AI is time independent. Yes?
We are considering a time independent lambda.
Yes.
How can you still say A0 is?
No, after we did that. So what we did is, first we used a Gage transformation to set A0 to 0. Thereafter, we use further Gage transformations involving time independent lambda, so that by doing those, A0 which was set to 0 remains 0 and AIs can change. And now we are trying to see what is the most useful lambda to change AI into a convenient form. So this is one equation. Now we need to see the other equation. Yes.
But you just have two constraints on lambda, right?
Yes.
But originally you just had one constraint, A0 dot.
No, A0 dot equals 0 we never had. When did we have?
Pi naught equals
Pi naught is equal to 0.
Yeah, so I just had one constraint. I'm going to a system of two constraints.
See, it's not that I am going to any constraints. There is an invariance. A mu goes to A mu plus del mu lambda. Okay, I am using all the freedom I am given to choose lambda. I can choose any lambda I like on any configuration and bring it to any other configuration which is related to it by del mu lambda. Up to me. Okay. So here what we see is that lambda can be used to set A0 equals 0, and now I will show you that after that, keeping A0 equals 0, it can be used to set something else to 0. Okay. I don't think you should use this. I don't think this is the same as counting the fact that there was a constraint pi naught equals 0. That doesn't even depend on A's at all, right? Pi is 0 just because the Lagrangian doesn't depend on A0 dot. Why are we getting this noise? Is something I'm doing? What?
Because the unit type.
This? But picking up what?
Now it's okay. Or maybe he was getting mobile signal.
No, I don't think it's mobile signal. I think it may be where I'm standing. Huh? The blackboard?
No.
Spot. Okay. ठीक है. Okay. Now that was one equation. This is a useful equation, so I put it in a box. Let's write the other equation. The other equation comes when you take the index nu equals I. So you get, or maybe better, j. So you get del 0 f0j plus del I fij equals 0. Now again let's evaluate this in the gauge where a0 is 0. So this first thing is just del 0 of aj. The second one is del I of aj. And the third term is minus del j of del I. Minus del I. Yeah, it was correct. Minus del j of del I ai. This is the equation. Now you see that both these equations, this one and the one on that side in a box, both have a term involving del I ai. Okay? And if del I ai could be set to 0, this equation would simplify very nicely into the Klein-Gordon equation for three components of A. A1, A2, A3. A0 is gone anyway. The other three would satisfy a nice Klein-Gordon equation. So it's tempting to try and set del I ai to 0. This suggests we should set del I equals 0 by a Gage transformation. So let's see if it's possible to find such a Gage transformation. How does del I transform under Gage invariance? Under Gage symmetry, it is del I plus del I lambda. I just take the divergence, 3 divergence of the Gage transformation, right? Now if I want the right side to be 0, then I find that del I lambda equals minus del I AI. What equation is this? It's a very familiar equation in physics. Wave equation. No, wave equations always have time in them. It's a Laplace equation. Actually, it's a Poisson equation because Laplace equation with a source on the right side is a Poisson equation. So here we won't go into too many mathematical subtleties, but hopefully this is some source. It's just like we have del squared something equals rho. This is like that rho. So it means that whatever configuration AI I was given, its 3 divergence is a source in terms of which I can solve lambda, and at the end I would have set, by using this lambda, I would have set del I AI equals 0. Now once I have done this, a very beautiful fact, this equation of motion says that del I AI is time independent. So if I set it equal to 0 by a Gage transformation at one time, it will remain 0 at all time. So that's the Coulomb gauge. We set A naught as well as del I AI to 0. Now one can do more and more analysis of it. In fact, one can carry out the entire quantization in this gauge, but that I don't want to do. I'll just make a couple more comments and then I'll switch to another gauge. Okay. So supposing we do all this, what are the final equations of motion? A0 is 0 and del I AI is 0. So that equation which I rubbed out is satisfied, this one. And this equation now reduces to the first 2 terms, which is box of AJ equals 0. How would we study this equation? If you've been here for my last 6 lectures, you should know. There are 3 wave equations of Klein-Gordon type. But still a problem because all the AJs are non-zero, A1, A2, A3, but they're subject to one constraint. The constraint has been used to get rid of this term, but the constraint still applies on these. So this subject to this. So somehow one would have to find a way to quantize the system subject to this constraint, and one way would be to introduce 3 sets of oscillators and then impose the constraint on the physical states and remove whatever is removed by that. Since it's one constraint, the actual answer is that there are only 2 independent oscillators by the end of it. Okay? And that means that the particle associated to this, the vector particle, has 2 independent polarizations And is that true of the photon? Yes, the photon has only two independent polarizations. Okay, so here we have it, that even though the original field had 4 indices, so naively it should have had 4 polarizations, but A naught was non-physical and we gauged it away very fast. So 3, then we had 3, but we still have this constraint, so we have 2, and 2 is the correct number at the end. But please see the apparent problem between Lorentz invariance and having 2 polarizations. See, a 4 vector has to have 4 components. There is no 4 vector which has only 2 components. But physical photon has only 2 components, while the 4 vector field has 4 components. How are these two reconciled? All by the effects of Gage invariance. So Gage invariance always removes 2 degrees of freedom. Now we'll see how these 2 degrees of freedom are removed in a different gauge. Well, let me also say one little thing. We can calculate, this I'm not going to do here. I don't know if the tutors are in a mood to do it. Maybe they've done it already. We can calculate the angular momentum operators Ji, J1, J2, J3 for the system just using Noether's theorem and rotational invariance of the system. From rotational invariance we get this, and yesterday Nemani explained to you Noether's theorem. So this for those who are not in, this is a side comment, so you don't have to go through it. But anyway, you can calculate these and then you can do the following. When you quantize this system, you can you have obviously the vacuum state, 1 particle, 2 particle, 3 particle. But let's act with these on the 1 particle state. Now 1 particle state cannot have orbital angular momentum simply. Okay? There is nothing to orbit around. So if you get any answer by calculating, for example, the total J squared on this, that answer must be the spin. And in fact you find that the spin T, or calculated by J squared, the spin of this field, of this state is h bar. That is 1 in units of h bar. So we learn that vector field describes spin 1 particle. Is this also something we know about the photon? In particular, we know from other less sophisticated analyses that the photon is a boson, so it must have integer spin. Spin is not 0, it's in fact 1. Okay, but now we see it as a prediction that every vector field has spin 1, and this prediction cannot be violated. Even the W plus, minus and Z bosons and gluons all come from vector fields, all have spin 1 for the same reason. Good.
Can you define J3 here? I thought the J vector is defined in the
Yeah.
frame of the particle.
Yeah, true.
It does not exist.
Alright, so the correct thing to define here would instead be the full Lorentz generators mu nu, which reduced to 3 rotation generators and 3 boosts. Rotation generators you certainly have, and that's good enough to measure angular momentum. This requires going through some amount of study of Lorentz algebra, which actually I'll do a little bit of it when it's needed, but for this purpose you probably have to write down some formulae. Another gauge in which we don't make a distinction between A0, A1, A2, A3, and in fact we do something which looks like the opposite. We make A0 dynamical and carry it along and get rid of it at the end. So for this, the starting point is to note that the Maxwell Lagrangian is minus half del mu A nu plus half, this I already showed you, this extra term created gauge invariance of this action. But as a choice of gauge, I could choose that this whole thing is 0, and this is called Lorentz gauge. It's different from Coulomb gauge because I am once and for all setting the 4 divergence to 0, not the 3 divergence. Okay. The advantage, if you want to call it that, is that now the Lagrangian is minus half of this, and therefore now there is a pi naught, and pi naught is just equal to minus a0 dot, or plus, I don't know, minus. Because we got rid of the thing which made pi naught 0 by a choice of gauge, so now there is pi naught. There is pi naught, pi 1, pi 2, pi 3. So there are 4 oscillators and one of them has negative norm. Okay. Now the strategy is different. So let me write this statement. So this looks like being back to the inconsistent theory I started with, but of course we are not back to that theory when we quantize this. Why? Why is this now possibly consistent? No, we have momentum, but we have negative norm states. Okay. Earlier also what is the difference between saying this is my Lagrangian or saying this is my Lagrangian, then I impose this gauge condition and now this is my Lagrangian? What's the difference between these two approaches? Yes, the mu in this still has to satisfy del mu equals 0. So I have to keep on using the fact that del mu is 0. That's my only hope. So for oscillators, one of them has negative norm, but when I implement del mu equals 0, all my problems should go away. Moreover, this is simply an alternate choice of gauge from Coulomb gauge. All choices of gauge should give me the same final physical answers. So if all goes well now in the next 10 minutes, we should again find that there are only 2 independent oscillators, but the language in which we describe them will be different because they are working in a different gauge. This is fine. What formations preserves Lorentz gauge? This is Lorentz gauge. What gauge transformations will preserve it? Those gauge transformations by a lambda such that box of lambda is 0. So this is no longer Poisson equation as we encountered earlier. This is, no, it's not Laplace equation, it is, Klein-Gordon equation. So lambda should satisfy the massless Klein-Gordon equation, then it preserves this gauge condition. Okay. Now we need to analyze this system in some detail, and it's always good in such analysis to move to momentum space. So in momentum space, instead of the gauge field, I have its Fourier transform A tilde mu of k. The gauge condition, this is the gauge field, is just the Fourier transform of the original one. The gauge condition is what? What is it? K mu A mu equals 0. And the residual gauge freedom is what? A mu tilde of k is equivalent to A mu tilde of k plus so we would have said del mu of lambda, so in this language it's k mu times some lambda of k. Okay, this is a general gauge transformation, but the only one which preserves this gauge is the one satisfying that equation on the right. Del mu of lambda equals 0. So in momentum space, okay, let's do it here. Is this with a constraint on this term, which is del mu lambda equals 0. What constraint is that? In momentum space, k squared equals 0. That is, we should only have those lambdas where k mu is 0. Okay, good. From an ordinary free theory without gauge invariance, one is that gauge condition gives me a constraint. The second is that there is a residual gauge freedom as long as k squared is 0. Which is this, I can shift a mu by k mu times any function as long as k squared is 0. Because then you see that this preserves the first gauge condition. So what we'll see now is that these two conditions or these two facts, one condition and one residual gauge freedom, remove 2 out of the 4 physical polarizations of the gauge field and leave us back to 2. This time we'll also be able to see something which we know intuitively. Which ones should be removed? If you have a wave propagating, then we know that the photon polarizations are transverse. So we should, if this is the 3 direction, we should remove the oscillator A3 as well as A0, keeping A1 and A2, and that's just what we'll do. Or it would have been this, except for these two properties which we have to implement on that. So the first property is that k mu on A dagger mu k 0 should be 0. Now what does it mean should be? This is of course not 0. This set of 4 states, I take linear combination of them. The condition says that this should be identified with 0. The gauge condition tells me that this state, though it's not 0, should be treated as 0. Wherever I see this state, I drop it. Let's give an analogy from vector analysis. Supposing I'm in a 3-dimensional room like this one, and I want to do everything in terms of shadows on the floor. Okay, every vector that I see in this room, I'll project it to its image on the floor. This you have done hundreds of times. What does projection mean? In practice, in terms of components of the vector, what do I do to project a vector onto a plane? Yeah, dot product is all very fancy. I've got a plane, okay, this is the z direction. All I do is wherever the vector has a z component, I put that by hand to 0. If the vector is vx, vy, vz, then the corresponding vector which is projected on the plane is vx, vy, 0. Same other components, vz component 0. It's in the same spirit that whenever any vector, state vector in this system has a component along this direction, I just set that to 0. That's what it means. So in this procedure, I actually take a full quantum system of 4 polarizations and I impose these two conditions afterwards. But after I have quantized, everything has become states in a Hilbert space. That's what quantum mechanics is. So to impose these conditions, I have to set certain states to 0. So I use this symbol, which means project all states in such a way that this component is 0.
Why not set the operator to 0?
You can't set an operator to 0 because then it wouldn't satisfy its own commutation relations. That's the whole point. You can't just set an because remember we quantize these by a dagger equals 1 or minus 1, so we can't set them to 0 anymore, but we can identify the states with 0. Let's see what the second result tells me. Okay, first of all, when I do this, let's choose k. We anticipate that k is going to be like, k squared will be 0. Okay, first let's, 0, 1 times a factor which won't have any effect. You can always choose a like k to point along the 0 and 3 directions. Okay, sorry, I choose k lower like this, so k upper is k 1, 0, 0, minus 1. So if I impose this on this, I see that the state A0 dagger on 0 is identified with A3 dagger on Z. So this is one constraint. If you like, it means that all states of the form A0 dagger minus A3 dagger on 0 are set to 0. So it's like projection onto that. So that's one step. What about the second one? Physical states. So we have to take linear combinations of the general state A mu k dagger on 0, and then from that we have to remove whatever is projected out. So first take an arbitrary linear combination psi mu A mu k dagger on 0, and now let's notice that A mu k is identified with A mu k plus k mu times some mode of lambda. This is the effect on oscillators. If I just break up this into oscillator modes, then I get that relation. Okay? But for this to be true, psi mu, k mu should be 0. That means only those polarizations of this are allowed for those psi's which are orthogonal to a like vector k. Not only that, the psi should not be proportional to the like vector k. Okay, in that case it will satisfy this equation, but that one is removable by Gage transformation. So these are the physical ideas, that polarization which has to be orthogonal to k mu, which is one condition. Polarization should not be along k mu. That's the second condition. So if I expand it, is psi naught, A naught dagger, psi 1, A1 dagger, psi 2, all this acting on 0. Now I have learnt that A0 dagger on 0 and A3 dagger on 0 should be identified. That's this relation. So I can write this. Oh, and also I think I solved, First let me solve this equation. This equation tells me that psi psi 0 plus psi 3 equals 0 with my choice of k. That's clear, right? Now you can see physically what's happening, and then I'll write it in terms of this space. Psi satisfies this relation, so psi 0 plus psi 3 is 0. But also, psi is not allowed to be parallel to k, which means that it would be of the form psi 0, 1, 0, 0, 1. That's also not allowed, because that's a Gage artifact. So what are the options left for a 4-vector psi? It should only have components in the directions 1 and 2. That's what I'm trying to show. What are 1 and 2? K is this. So 1 and 2 are the transverse directions. The beam is propagating in the z direction. If I want to work that out on this, I use this relation to rewrite this as psi 0, A dagger 0K minus A dagger 3K on 0 plus the other two terms. So this came because I used psi 3 is minus psi 0, so I got this. But this state is set to 0 by this condition. So at the end we see that we have only two polarizations proportional to the vector psi 1 and psi 2. And these are the transverse polarizations of the photon.
Can we say that the longitudinal photon has eaten up the scalar photon and the
But there was no scalar photon. Oh, longitudinal and scalar, I see. Yeah, perhaps you could actually, I don't know. Maybe. The main thing to notice here is we never broke Lorentz invariance while setting the Gage condition up, but we chose a vector k mu. Of course, any choice of a vector k mu will break Lorentz invariance, and it being a light-like vector, it's natural always to choose it in time and one space direction. So that establishes the time as separate as well as one space direction as the direction of the beam. Okay, so that breaks Lorentz invariance, and finally the only psi's which are allowed are the ones with components in these two places, which are the transverse components. Well, yeah, this is true in the sense that all these things concern external on-shell particle states. And to the extent external states also propagate freely till they interact, then it's still true. In the interaction, of course, you have all momenta, not only k squared equals 0, and then you'll have all polarizations. So that is certainly true. So these virtual particles, you could say that they also propagate negative momenta, negative probabilities. There's no problem with that, as long as at the end all the bad effects cancel each other out, which can be shown by some heavy duty techniques in field theory. However, in the Coulomb gauge approach, if you take it to its logical extreme,
non-locality, whatever you can still show that the non-local terms cancel.
Correct.
Each order and you still gain.
That's correct. That's correct. So the end result is, of course, that whatever legitimate way you use, this is the statement of gauge independence. Any way of solving a gauge theory, if it's correct, will give the same physical answer. But the price you pay is that in Lorentz gauge, at intermediate stages, you have particles with negative probability propagating in loops and all that. And if you remove all the unphysical degrees of freedom, then you have some non-local interactions, but the final interaction is still local. The net interaction is local. Non-locality drops out.